Hi, this is Jason Baker, and welcome to week 12 of our DevOps and Cloud Infrastructure course. This week, we are going to talk about containers, and containers are one of the most exciting subjects, I think, in this course. Many students who have signed up for this course and taken it over the years have told me that one of the main reasons they wanted to take this class is because they wanted to work with containers and work with Docker technology. And this technology is totally transforming IT today. It's changing the way that we package and deploy our applications. And I think it's a fantastic technology. I in my organization we use Docker and containers extensively. We use it as the packaging mechanism for nearly all of our applications. And it offers tremendous benefits over the traditional processes of trying to package applications. So let's look at the agenda for this lecture. I'm going to talk a bit about containers from a theoretical standpoint and give you an understanding of the purpose and the benefits of containers. And I'll also try to give you an understanding of the differences between containers and virtual machines because oftentimes people confuse these two technologies because there are similarities, but there are also very clear differences between the two. And then much of the lecture is going to be spent on a containerization technology called Docker, and I'll provide you with an overview of the Docker architecture. We'll look at a number of the Docker client commands. We'll look at something called a Docker file, which we can use to describe how a Docker image is built. We'll build a Docker image, and then we'll kind of wrap things up by looking at some of the more advanced topics in Docker. We'll look at Docker networking and how Docker manages volumes. So let's jump right in. The lecture is going to involve some um, hands-on execution of Docker commands, and so you can feel free to try these Docker commands yourself. I have provided you with a CloudFormation stack that you can use to launch a single AWS EC2 instance, and that EC2 instance has the Docker engine installed. An alternative is that you could also install Docker on your Windows or your Mac system. There's a Docker for Windows and Docker for Mac software freely available that you can download and install on your laptop as well. So one of the challenges we face in IT traditionally is that oftentimes we're dealing with many different application stacks in our environment. We might have like a static website application that's running on Nginx. We might have some sort of message queue, using something like maybe Redis. We might have an analytics stack that is running Hadoop and maybe Spark. We have a web API built using Python and the Flask framework. So we have all these different application stacks in our environment that we need to manage. We might have dozens of these. If we're working at a large company, we might have hundreds of application stacks that we need to maintain. And at the same time, we need to be able to deploy these application stacks to many different environments. We have development machines that might be virtual machines. We have quality assurance and testing servers. We have production servers that might be sitting in a data center somewhere, or maybe we have EC2 instances we need to deploy our application stacks to in the cloud. And finally, we have application developers who are, the developers are actually kind of building these application stacks, and they might be deploying the stacks on their local workstation. Well, what this leads to ultimately is what we call the matrix from hell, which is a situation where we have these application stacks and we need to be able to deploy each application stack to nearly every different type of environment that we need to support in our organization. So our analytics stack has to be deployed to a development environment, a quality assurance environment, the public cloud, a developer laptop. So every single one of these application stacks likely needs to be deployed in all of these different environments. And so now we need to try to accommodate all of these different scenarios, and it becomes extremely challenging because the way we deploy at least traditional software on one type of system might be slightly different than the way we deploy it on a different system. And those two different environments, they might be configured differently. They might have slightly different versions of the operating system, slightly different software packages and shared libraries. And so there's subtle differences between these systems, and that creates a tremendous amount of complexity. Well, what's interesting is that the challenges we face in IT are very similar to the challenges faced by the cargo transportation industry before the 1960s. So before the 1960s, if you were transporting goods across the world, you were dealing with a situation where you had many different types of products that you might need to be transporting, everything from bags of grain to automobiles to uh, to drums of oil and boxes, crates, and full of product. And then you would transport these goods using a variety of different transportation methods, everything from ships to trucks to trains. And you might have to use like a forklift to get product off of a truck onto another truck or onto a train. So it was a challenging process, and there were a lot of challenges in trying to figure out how do you get a a a product from one part of the world to another part of the world and move it across all of these different transportation methods. Well, so and the cargo transportation industry, then they faced their own matrix from hell, right? Because they had to try to figure out, well, how do we transport any one of these products on any one of these different transportation methods? They came up with a very interesting solution, which is called the intermodal transport solution. Essentially, they they the transportation industry worldwide got together and decided to build a common intermodal shipping container, which means that they agreed upon a standardized shipping container size, and this shipping container size is designed to fit on a variety of different transportation platforms, anything from ships to trucks to trains. And today, over 90% of all of our cargo worldwide is shipped in these intermodal shipping containers. And I'm sure that every one of you has seen one of these. You've seen these on a train, or you've seen them on cargo ships, or you've seen them on trucks. And these containers can be lifted right off of a cargo vessel, of a shipping vessel, and dropped right on right onto a truck and then trucked off to a destination, or they can be lifted and put right on onto a train. So um, this greatly reduced the complexity associated with shipping products around the world because now these transportation companies didn't have to worry about, how are they gonna move a product from one transportation uh, platform to another transportation platform. There's over 5,000 large cargo vessels that are delivering over 200 million containers per day. And these containers contain everything from grains to the latest electronic toy to oil drums to automobiles. Here are some pictures of intermodal shipping containers. And again, I think everyone has seen these containers, going down the road on the back of trucks or on the decks of large shipping vessels. So the IT industry looked at this solution and said, "Hey, I think that this might actually apply to the challenges that we face. We have these different types of applications, and we need to be able to ship them or deploy them into different types of environments. And if we could basically put our application stack into some sort of container, then all we would have to be worried about is moving containers around because the container would be stored and shipped the same way on any sort of environment. And so in the IT industry, we came up with a solution, a transportation solution called containers. And it's really the equivalent of the intermodal shipping container. A container encapsulates an application stack in a lightweight and portable environment. Um, and the container itself can be deployed on most any type of environment in our IT organization. Um, and so the servers that are running these containers, they're not they're focused on providing an environment for the container, and we don't have to worry as much about what is actually inside of the container. So then our IT matrix from hell is solved by containers because every single one of our application stacks, we can build that into a container, and instead of deploying the application stack to the environment, we're actually deploying a container to the environment. And the container is the same. So the container that I run on my developer laptop is absolutely identical, bit for bit, to the container that I deploy on my production server. And that is an absolutely huge win because one of the big challenges we face is that when we build applications, they oftentimes will run slightly differently depending on which environment they're deployed. With containers, that's not the case. So from a developer perspective, the big benefit is that you can build an application stack once, build it into the container, and then now you can run that application stack anywhere, and it will run identically on every single environment. So you're eliminating any concerns about compatibility on different hardware platforms in your environment. Your application stack will run the same way on the dev environment, testing environment, and at your customer site. You don't have to worry so much about the different application dependencies. A lot of times when you install software in a system, you have to have the system needs to have some required packages installed. There's some shared library dependencies, And you don't have to worry about those because those dependencies now are actually built into the container. And every single application runs inside of its own container. It's its own, think of it as its own. It's like the application is running in its own little bubble. And inside the bubble, it has everything it needs to run that application. It has the right file system structure. It has all the correct application dependencies. And so you eliminate then different conflicts between applications because traditionally you might try to install two different applications on the same system, and each application might require a different version of the same shared library. And so that would create these conflicts. Well, that's easy to accommodate in containers because each application is installed into a container, and each container can can contain its own version of any shared library dependency. And the containers also make it really easy to automate testing and deployment processes using scripting because now instead of trying to figure out how do we install software on a particular system and how do we install all the dependencies and set up all the configuration properly, and you might have like dozens of different steps that you need to perform to get software installed on a system. Well, now you can just install it all into a container, and it's absolutely trivial to then move that container from one system to another, and it's trivial to deploy the container on a system. You don't have to worry about a myriad of different uh, deployment and configuration steps. And then finally, containers are very, very lightweight. They don't require much overhead from a system resource standpoint, and they're much more lightweight than something like a virtual machine. And well, I'll talk about why shortly. From an IT operations perspective, uh, the containers are also hugely beneficial because the we can take a container and we can deploy it on any environment, and that container will run the same way. It eliminates all the inconsistencies that you experience between the different environments in your organization. One of the big challenges that we would face from an operations perspective traditionally is that we the development team would create this new application stack, and they would deliver it to us, and then it was our responsibility to deploy it in some environment. And inevitably we would deploy the application stack in an environment and it wouldn't work properly. And then we go back to the development team, and the development team would just sort of like shrug and be like, well, it worked just fine for us. It worked just fine in our development workstations. We don't know why it's not working in the production environment or the testing environment. And so containers eliminate that, because if the container runs in the development environment, if it runs on the developer's laptop, it will run the same way in the production environment. So greatly simplifies things like continuous integration, simplifies the deployment of our applications. And also because they're lighter weight, they also help to alleviate some of the overhead and financial costs associated with running virtual machines. So from a high level perspective, now you understand what a container kind of does and what are some of the benefits of containers. But from a technical perspective, well, what is a container exactly? So a container feels very much like a lightweight virtual machine. You can log into a container and access a shell within the container. Each container has its own process space. So you can log into a container and you can see one or more processes running. You can shell into the container and you can run commands within that container. You can install software packages inside of the container. You can run services. Each container has its own network stack. So when you're inside of a container, you can look at like Ethernet interfaces, and you can assign IP addresses and so on. So a container feels like a virtual machine in many ways. However, from a low-level standpoint, a container is not like a virtual machine, and it isn't a virtual machine because a container doesn't have its own operating system. A container uses the underlying host kernel, and this is extremely important to understand. A container does not have its own operating system. A container uses the underlying host kernel. Unlike a virtual machine, right? A virtual machine has its own operating system, and that could be completely different than the host, that's hosting the virtual machine. The container can't run a different operating system than the host. A container could run a different like Linux distribution. You might have a host that is running, let's say, the Ubuntu Linux server, and a container might be running, let's say the container might be running a CentOS Linux distribution, but they're still both using this exact same Linux kernel. Um, they're essentially using the same operating system. They might just have a slightly different distribution. The container can't load its own kernel modules because again, it's using the host operating system and the host kernel. The container can't emulate devices like USB ports or special storage interfaces and so on. In a virtual machine, we can emulate all that hardware, right? We're faking out the operating system and tricking it into thinking that there are all these different hardware components because we're emulating that hardware. We can't do that with a container. Um, the the container itself doesn't need to run many of the OS type processes that are running on the host because the container isn't running its own operating system. The container is piggybacking on the host operating system. And one of the ways to look at a container is I look at a container as being like a super process. It's a very specialized process that is running on a system. It's a process that has its own process space, its own file system, its own networking stack. It's kind of similar to what we call chroot, or sometimes they're referred to as jails on like old FreeBSD systems that have jails. It's very similar to that sort of concept where we have a super process which is sort of fenced off from the rest of the other processes on the system. And here's a diagram showing some of the differences between a virtual machine and containers. On the left-hand side, we have a virtual machine. And in this case, this is like a type 2 hypervisor. So we have our server, and the server is running a host operating system, like let's say it's running Linux, and then we have a hypervisor. That hypervisor could be like VirtualBox, and then we're running guest OSs, and these guest OSs could be Linux, they could be Windows guest OSs, they could be a variety of things. And what's important here is that each virtual machine has its own operating system. installed. It's a complete operating system for each VM. And then we have our shared libraries and binaries and our applications installed on top of the guest operating system. Now, in a containerized system, we have our physical server, we have our operating system, which could be, in most cases is Linux operating system when running Docker. And then we have something that's kind of similar in some ways to a hypervisor. In this case, we're using a Docker engine. And this is the Docker engine is going to sort of manage the containers that are running on the system. And then on top of the Docker engine, we have our containers, and each container has a set of shared libraries and a file system and our application. Note what is missing here. There's no guest operating system installed on any of these containers. The containers are using the underlying operating system. So I can't install a Windows container on my Linux operating system. The container is using the same operating system, the same kernel as the host. And it's not that it's made a copy of that stuff, it's literally using the exact same kernel because this container is not a virtual machine. This container is a super process. It's a highly specialized process that is running on that operating system. So, what are some of the advantages of containers over virtual machines? What can a container do that a virtual machine can't? Well, there are several advantages. One is containers are much more lightweight. They're much easier and much easier to deploy, much simpler to deploy than a traditional virtual machine. A container can oftentimes boot and start up in a fraction of a second compared to, it might take you 30 seconds, it might take you a minute or longer to boot up a virtual machine because it's literally like you're booting the operating system, you're starting it up. It's like you're booting up a server. A container is like a process. So it's like you're starting up an application on your system, and the application can oftentimes boot up in seconds. The containers are much more granular than virtual machines because virtual machines include a big operating system stack and they include all the applications and so on. Containers are generally much smaller, much granular. Typically, when we're building a container, that container is only running a single process. That's the very common pattern that you'll find in the marketplace, where each container is running a single process. So these containers are very granular, and they align well with microservices architectures. And then lastly, because containers are much more lightweight and have a smaller footprint, that can greatly reduce the amount of resources needed in a testing or development environment.